An estimator is a random variable, so a coefficient alone cannot tell us whether an apparent effect is real. We also need a trustworthy sampling distribution and standard error. When errors change variance or move together over time, the familiar formulas can fail. Our task is to conduct reliable inference under heteroskedasticity and serial dependence. We begin in the frequency domain, where long-run variation can be understood through the spectrum. The chapter's methods form a connected toolbox. Heteroskedasticity and autocorrelation consistent, or HAC, estimators target the long-run variance consistently. Fixed B asymptotics and self-normalisation use different limiting approximations to improve inference when dependence is persistent and samples are finite. Bootstrap and subsampling approximate distributions through repeated data-based calculations. The generalized method of moments, or GMM, turns economic moment restrictions into estimators and tests. Each method handles dependence differently, so its assumptions must match the application. The long-run variance summarizes the cumulative contribution of contemporaneous variation and serial covariance. It controls the large sample variability of sample, means, regression scores, and many moment estimators. One way to view it is as a sum of autocovariances. Another is through the spectrum at frequency 0. The two views are mathematically equivalent, but each gives different intuition. The time domain emphasizes dependence across lags, while the frequency domain emphasizes how variation is distributed across cycles of different lengths. A periodic function repeats after a fixed interval. Sine and cosine waves are the basic building blocks for representing periodic behavior. A sinusoid is described by amplitude, frequency, and phase. Amplitude controls the height of the oscillation. Frequency controls how quickly cycles repeat. Phase determines where the cycle begins. Complex economic series are not usually single perfect waves, but spectral analysis represents their second-order behavior as a combination of components operating at different frequencies. Autocovariance measures the association between observations separated by a given lag. The spectrum reorganizes the same second-order information by frequency rather than lag. High spectral density near a frequency means that cycles around that frequency make a relatively large contribution to variance. Low frequencies correspond to slowly changing components and long cycles. High frequencies correspond to rapid alternation. For a stationary process with suitably summable autocovariances, the spectrum is real, non-negative, symmetric, and fully describes the covariance structure. The spectral representation theorem formalizes the idea that a stationary process can be decomposed into orthogonal frequency components. Euler's relation links complex exponentials to sine and cosine waves, making Fourier methods convenient. We do not need to interpret imaginary numbers as economic quantities. They are an efficient accounting device that carries amplitude and phase. After the symmetric components are combined, the spectrum of a univariate stationary process is real and non-negative, as a measure of variance must be. White noise provides the simplest benchmark. Its autocovariance is 0 at every non-zero lag, so it has no preferred cycle. The spectrum is therefore flat across frequencies. This does not mean that a particular realization looks perfectly featureless. A finite sample can display temporary patterns by chance. The flat population spectrum says that, on average, variance is spread evenly across frequencies. Comparing an estimated spectrum with this benchmark helps identify persistence, seasonality, or short-run alternation. A pure sine A wave lies at the opposite extreme. Its variation is concentrated at one frequency and the corresponding negative frequency used by the mathematical representation. Spectral mass is therefore concentrated rather than spread smoothly. The Dirac delta is the idealized device used to describe that concentration. Real economic series usually combine broad stochastic components with possible narrow seasonal peaks. A sharp periodogram peak may suggest a cycle, but finite sample leakage and multiple testing mean that it should not be interpreted mechanically. Linear filters reshape spectra in a transparent way. A moving average process combines current and past shocks, and its spectrum equals the innovation spectrum multiplied by the squared magnitude of the filter. An MA1 process can emphasize low or high frequencies depending on the sign of its coefficient. An autoregressive process creates a different transfer function. A positive, persistent AR1 coefficient places substantial power near frequency 0, reflecting slow movement and long-lived dependence. For a general ARMA process, the autoregressive and moving average polynomials jointly determine how white noise is transformed across frequencies. Peaks indicate frequencies amplified by the dynamics, while troughs indicate frequencies attenuated. This representation is useful because complicated autocovariance sequences can have simple spectral shapes. Stationarity and invertibility remain important for interpretation. A formula that evaluates numerically is not enough if the assumed dynamics place roots in regions that invalidate the stationary representation. In a sample, we first estimate autocovariances and then form the periodogram, a frequency-by-frequency measure of sample variation. It can also be understood through regressions of the observed series on sine and cosine terms at Fourier frequencies. The resulting squared coefficients show how strongly each frequency appears in the sample. This regression interpretation makes the periodogram intuitive, but it does not turn every peak into a stable deterministic cycle. Random series also produce uneven sample periodograms. The raw periodogram is asymptotically unbiased at many frequencies under regularity conditions, yet it is not a consistent estimator of the spectrum at a fixed frequency. Its variance does not vanish as sample size grows because each ordinate remains noisy. This is a crucial warning. A denser frequency grid does not make an individual ordinate precise. Consistency requires averaging information across nearby frequencies, or equivalently, tapering sample autocovariances across lags. Spectral estimation is therefore another smoothing problem. Integrated mean-squared error explains the role of smoothing. Averaging more neighboring periodogram ordinates reduces variance, but can blur a spectrum that changes sharply with frequency. Averaging too little preserves local detail, but leaves substantial noise. A frequency bandwidth regulates this trade-off. The corresponding time domain lag window does the same job from the other direction. We choose smoothing for the inferential target, especially behavior near frequency 0, rather than seeking the most visually dramatic spectral graph. In R, start by removing a justified mean or deterministic component and checking whether stationarity is plausible. Plot the series and sample autocorrelations before estimating a spectrum. Record the frequency convention and sampling interval, because a frequency only becomes an economic cycle after conversion into time units. Compare the raw periodogram with several smoothed versions and treat edge behavior carefully. Reproducible analysis should state the taper, smoothing span, and any detrending, rather than relying silently on defaults. The chapter case uses annual United States real gross domestic product growth from 1960 through 2024. Because observations are annual, a spectral peak cannot be interpreted as monthly seasonality. The smoothed estimate places substantial mass at low frequencies, consistent with medium and long business cycle movements, but the short sample limits precise claims about any one cycle length. Now, let me show you the bridge to robust inference. The long-run variance is proportional to the spectrum at frequency 0, the place where very slow fluctuations pile up. Serial correlation can make that value far larger or far smaller than the one-period variance, and conventional standard errors quietly ignore this cumulative structure. HAC methods estimate that zero-frequency behavior by smoothing autocovariances or periodogram ordinates. In the next lesson, we build those estimators and see why positive semi-definiteness, pre-whitening and weighting all matter. We now turn from spectral foundations to heteroskedasticity and autocorrelation-consistent inference. In a linear regression, estimated by ordinary least squares, or OLS, the coefficient error depends on sums of regressors multiplied by disturbances. These products are often called scores. If scores are heteroskedastic or serially correlated, the usual homoskedastic variance formula is wrong. Robust inference therefore focuses on the long-run covariance matrix of the score process, combined with the familiar regressor moment matrix. The long-run covariance adds the contemporaneous score covariance to covariance terms from every positive and negative lag. Positive serial covariance makes accumulated scores more variable, while negative covariance can calm them down. That is why robust standard errors are not automatically larger than conventional ones. It depends on the dependence structure. A correct standard error simply describes sampling uncertainty. It is not a penalty that must always inflate a result, so when it comes out smaller, treat that as a prompt for diagnostics, not an automatic rejection. The frequency domain provides an equivalent definition. The long-run covariance is proportional to the score spectrum at frequency 0. Slowly moving score components are especially important because they accumulate rather than cancel in sample averages. Estimating the long-run covariance is therefore the same basic problem as estimating a spectral density at 0. We can combine sample autocovariances across lags or average periodogram information near 0. The two constructions are linked by Fourier transformation. A direct sum of all sample autocovariances performs poorly because long lag estimates are extremely noisy. HAC estimators control that noise by applying weights that decline with lag and by truncating or effectively shrinking distant terms. The NUE West estimator uses Bartlett weights, which fall linearly from 1 at lag 0 to 0 at the selected cutoff. This produces a consistent estimator under suitable conditions when the cutoff grows with sample size, but remains small relative to it. The lag cutoff, often called a bandwidth, determines how much dependence is included. A short bandwidth may miss economically relevant serial correlation and bias the long-run variance. A long bandwidth includes more distant sample covariances, but raises variability because those covariances are estimated imprecisely. The best choice depends on persistence, sample size, kernel, and inferential objective. A universal lag number cannot be justified merely because it is a software default or common convention. The covariance window view makes the estimator concrete. Compute residual-based scores, estimate their covariance at each lag, multiply each covariance by a kernel weight, and add the weighted terms symmetrically. Residuals introduce estimation effects, but under standard conditions they provide valid sample analogues. The construction extends from one coefficient to a matrix of moments. Care is needed with centering, degrees of freedom choices, and the exact definition of lagged products, because packages may implement small sample adjustments differently. A covariance matrix used for standard errors should be positive semi-definite. Without that property, an estimated variance could be negative, or a quadratic test statistic could behave nonsensically. Some time domain weight sequences do not guarantee positive semi-definiteness in finite samples. The spectral view clarifies the solution. Non-negative frequency weights produce a positive semi-definite weighted periodogram estimator. Bartlett-based Newey-West weighting has this desirable property. Valid asymptotic order alone does not guarantee a well-behaved finite sample matrix. Pre-whitening can improve estimation when the score process is strongly persistent. Fit a low-order vector, auto-regression to the scores, estimate the long-run covariance of the less dependent residual process, and then reverse the filter to return to the original scale. The aim is not to claim that the fitted autoregression is the economic model. It is a numerical device that flattens the spectrum near zero. Poorly estimated or unstable pre-whitening filters can instead add error, so diagnostics remain essential. The Cochrane or cut idea gives a familiar univariate analogy. Estimate a first-order autoregressive pattern in regression errors. Transform the equation to reduce serial correlation and refit. Traditional feasible generalized least squares uses the transformed model to change coefficient estimation. HAC, pre-whitening, instead uses a filter to improve long-run variance estimation while preserving the primary estimator's interpretation. Confusing these objectives can lead an analyst to report a different coefficient without recognizing that the estimation target or assumptions have changed. The periodogram is formed from discrete Fourier transforms of the score process. Near frequency 0, each raw ordinate is noisy, so we combine neighboring ordinates with non-negative weights. Multiplying the weighted average by the appropriate normalization gives a frequency domain estimator of long-run covariance. Because each periodogram matrix is positive semi-definite, a non-negative weighted average remains so. This geometric fact is one reason the frequency domain is more than an alternative notation. Weighted periodogram and sum of covariances estimators are two faces of the same operation. A weighting window in frequency corresponds to a kernel over time lags, and vice versa. A sharply bounded window in one domain generally creates oscillatory weights in the other. This duality explains why an apparently simple choice can have subtle consequences. We should inspect both the implied lag weights and the frequency response when evaluating whether an estimator emphasizes the dependence relevant to the application. For regression inference in R, estimate the model first, then construct a score for each observation from the regressor vector and residual. Choose a HAC routine whose kernel, lag rule, and finite sample correction are documented. Compare conventional, heteroskedasticity robust, and HAC standard errors, but do not choose among them based on which produces significance. Plot residuals and score autocorrelations. If conclusions depend sharply on one lag choice, that instability is part of the empirical finding. The chapter implementation also applies Newey-West estimation to daily DAX log returns. The routine reports a normalized long-run variance, and multiplying by sample size gives the variance scale of the cumulative sum used in the partial sum display. This scaling distinction matters. The long-run variance of one normalized average and the variance of a full cumulative total are not the same numerical object. Interpretation should focus on the hypothesis and data frequency. Monthly macroeconomic errors may remain related across many months, whereas high-frequency returns can have weak mean autocorrelation but strong dependence in squared values. HAC, corrections for a mean equation, respond to dependence in its score. Not every visible feature of the raw series include deterministic terms, seasonality, and transformations appropriately before relying on a covariance estimator to repair model misspecification. Robust standard errors do not make a wrong conditional mean correct. Finite sample corrections differ across implementations. Some divide lagged covariance sums by the full sample size, others by the number of available pairs, and some rescale the final sandwich for degrees of freedom. These differences vanish under standard asymptotics, but can matter in a short sample. Reproducing one result requires matching the exact score, normalization, kernel, bandwidth, and correction. So here is what I want you to hold on to. HAC, inference, keeps coefficient estimation separate from measuring its uncertainty. The long-run covariance gathers up the dependence in the score process, and kernel weighting is what makes that gathering feasible. Positive semi-definiteness protects the geometry of our variances, and pre-whitening can tame difficult persistence, but none of this removes sensitivity to the bandwidth. So next I will look at kernels and bandwidths directly, and show how choices in the time and frequency domains trade off bias, variance, and test size. Kernel weighting in long-run variance estimation operates simultaneously in two domains. In the time domain, the kernel assigns weights to sample autocovariances by lag. In the frequency domain, its Fourier transform determines how periodogram ordinates are averaged. A narrow window in one domain corresponds to a broad pattern in the other. Understanding this duality prevents us from treating kernel names as arbitrary menu choices. Each kernel encodes a particular compromise between retaining structure and suppressing noise. The truncated kernel gives equal weight to all autocovariances through a cutoff and zero weight afterward. Its abrupt edge creates an oscillating frequency response that can take negative values. This may yield a long-run variance estimate that is not positive, semi-definite. The estimator can have relatively low bias when dependence ends sharply, but high variability and unstable finite sample behavior are common. Simplicity of the lag rule is not the same as reliability of the covariance matrix. The Bartlett kernel decreases linearly with lag and reaches zero at the cutoff. Its frequency response is a non-negative squared sync shape, so it supports positive semi-definite estimation. This is the kernel underlying the familiar Nu-E West procedure. Tapering distant autocovariances reduces the discontinuity created by hard truncation. The price is additional bias if important dependence receives low weight. Bartlett weighting is a sound baseline, but it is not automatically optimal for every spectrum or inferential target. The Daniel kernel illustrates the duality in the opposite direction. A flat averaging window over nearby frequencies corresponds to a sync-shaped oscillating pattern over time lags. Frequency averaging is easy to interpret as a low-pass operation, but the implied time weights include negative regions. Those negative weights do not necessarily make the estimator invalid when the frequency weights remain non-negative. The relevant positive semi-definiteness condition is clearer when we inspect the estimator in the domain where it is constructed. The Parson kernel is a smooth, piecewise polynomial taper that stays within a fixed range of lags. Its frequency response decays smoothly and never turns negative, so stronger smoothing lowers variance, though it can add bias if the spectrum bends sharply near zero. The quadratic spectral kernel is a useful alternative. Its lag weights reach out without a hard cutoff and oscillate as they fade, while its frequency shape is a compact parabola. Under standard smoothness conditions, it has attractive mean squared error properties, which is why many people reach for it instead of Bartlett. Kernel choice matters, but bandwidth usually matters more. In the time domain, increasing the lag bandwidth includes more sample autocovariances. This reduces truncation bias when dependence is persistent, but raises variance because long lag covariances are noisy. In the frequency domain, averaging more nearby ordinates reduces variance, but can increase bias by mixing frequencies whose spectra differ. The two bandwidth conventions move in opposite verbal directions, so always check how a particular package defines its tuning parameter. A flat frequency window makes the trade-off especially visible. Average a group of periodogram ordinates centered near frequency 0. A wider group stabilizes the estimate because more ordinates contribute, but it may include frequencies that do not represent the 0 frequency value well. The corresponding lag kernel stretches over fewer or differently weighted autocovariances. This reciprocity means that statements such as larger bandwidth means more smoothing are ambiguous, unless the domain and parameterization are specified. For consistency, a lag bandwidth generally grows with sample size, so progressively more dependence is captured, while its ratio to sample size goes to 0, so very noisy, distant lags do not dominate. That asymptotic requirement leaves many finite sample choices. Plugin selectors estimate persistence and spectral curvature before choosing a bandwidth. Rule-based selectors use reference dynamics. Both can be useful, but neither is immune to structural breaks, near unit roots, seasonal dependence, or an inaccurately specified pilot model. Mean squared error combines squared bias and variance, providing one criterion for bandwidth selection. An estimator with good mean squared error need not produce well-sized tests. Hypothesis testing is sensitive to bias itself, because a systematically understated long-run variance leads to excessive rejection. With moderate serial correlation, conventional HAC tests can reject a true null too often. Inference, therefore, requires judging coverage and size, not only the numerical accuracy of the variance estimator. This distinction explains a difficult practical tension. Including more lags can reduce bias in persistent data, which helps test size, but it raises estimator variance and can weaken power. Including fewer lags creates a stable-looking standard error that may systematically omit dependence. There is no tuning choice that removes the trade-off. Sensitivity across defensible bandwidths, combined with evidence about persistence, is more honest than selecting the lag that makes a preferred coefficient cross a significance threshold. Positive semi-definiteness, consistency, and low mean squared error are desirable properties, yet they do not fully determine finite sample inference. A positive semi-definite matrix can still be badly biased. A consistent estimator can converge too slowly to be reliable in the available sample. An asymptotically efficient kernel can deliver poor coverage under strong dependence. Robust inference is therefore not a box checked by invoking New West. It is a chain of assumptions, tuning choices, diagnostics, and critical value approximations. In R, compare at least a small set of principal choices such as Bartlett and quadratic spectral kernels with documented automatic bandwidth selectors. Preserve the same coefficient estimate while changing only the covariance calculation, unless the research design calls for another estimator. Record whether pre-whitening and finite sample adjustment are enabled. A table of standard errors across choices is often more informative than many significant stars. Plot the implied lag weights so readers can see which dependence the estimator retains. Automatic bandwidth formulas use a pilot estimate of serial dependence and therefore add another estimation layer. A nearly unit autoregressive pilot can produce a very long bandwidth, while a poorly fitted pilot can miss important lags. Inspect the selected number in calendar units and compare it with nearby values. Automatic means reproducible, not assumption-free. When your data sit on an economic calendar, let the calendar guide how you read the bandwidth. 12 monthly lags span a full year, but 12 daily lags cover less than 3 trading weeks. Seasonal peaks can make a smooth zero-frequency approximation misleading if you have not first dealt with deterministic seasonality. And a structural break creates low-frequency power that a HAC estimator may mistake for persistent stationary dependence. No kernel can tell you whether a slow movement is a break, a trend, or a genuine cycle. That judgment about the model has to come first. Confidence interval coverage is the practical consequence of test size. If the estimated long-run variance is biased downward, nominal 95% intervals can cover the truth far less often than 95%. Reporting sensitivity across kernels and bandwidths reveals this risk, but it does not restore exact coverage. Resampling, fixed B, or self-normalisation offers alternative approximations when dependence is strong. Let me be clear about the moral here. I am not telling you to abandon HAC methods. They are indispensable, and they often work well. My point is narrower. Their normal or chi-squared approximations can be inaccurate when the long-run variance is estimated noisily. One good response is to use a normalizer that stays random in the limit, and then adjust the critical values to match. Fixed B asymptotics does exactly that, and it is where we go next. Fixed B inference begins from a finite sample weakness of conventional HAC methods. Standard asymptotics let the lag bandwidth grow, but require its fraction of sample size to vanish. This is called small b asymptotics. In an actual sample, the selected fraction may be far from zero, especially when strong dependence requires many lags. Small b, critical values, then ignore uncertainty created by estimating the long-run variance with a substantial bandwidth. Fixed b asymptotics keeps that fraction positive in the limit. There are two broad responses to distorted HAC tests. One is to estimate the long-run variance more accurately under stronger assumptions. The other is to accept a deliberately inconsistent normalizer whose random limiting behavior can be characterized. Fixed B takes the second route. The variance estimate does not converge to one fixed population matrix in the usual way. Instead, it converges to a random functional that is stochastically proportional to the true long-run covariance. This apparent inconsistency is useful because the same unknown long-run covariance appears in both the coefficient limit and the normalizer limit. After forming an appropriate test statistic, the nuisance covariance can cancel. What remains is a pivotal distribution involving Brownian motion, the kernel, and the bandwidth fraction. Critical values are therefore different from standard normal or chi-squared values and generally depend on B. Using conventional critical values would discard the very correction fixed. B is designed to provide. Consider OLS regression and define a score at each date as the regressor multiplied by the disturbance. Partial sums of these scores drive coefficient uncertainty. A functional central limit theorem states that the entire rescaled partial sum path converges to Brownian motion transformed by a long-run covariance factor. This path result is stronger than an ordinary central limit theorem at the final date. It lets us analyze covariance estimators that depend on partial sums throughout the sample. A second assumption concerns the cumulative regressor design. Normalized sums of regressor outer products over each sample. Fraction should converge uniformly to that fraction times a positive definite matrix. This ensures that the regression geometry stabilizes along the whole path. Together with the functional central limit theorem, it yields the familiar asymptotic normality of OLS when the true long-run covariance is known. The inferential difficulty lies in estimating that covariance accurately from dependent data. A kernel HAC estimator sums weighted sample score autocovariances. Under small b asymptotics, the bandwidth fraction shrinks to 0, and the estimator converges to the true long-run covariance. Under fixed b, the bandwidth remains a fixed fraction of the sample, and the estimator converges to a random matrix functional of Brownian motion. The matrix reflects both the kernel and b. It retains first-order information about smoothing uncertainty that small b asymptotics suppresses. The fixed b test statistic combines the coefficient deviation with this random covariance estimate. Its limiting distribution is generally non-standard, but it is free of the unknown long-run covariance under suitable conditions. Simulation can generate critical values from the corresponding Brownian functionals. Larger b often improves size control because it acknowledges more covariance estimation uncertainty, but it can reduce power. This is a genuine trade-off rather than a universal instruction to choose the largest possible bandwidth. Calling fixed b pivotal requires care. The limiting law may still depend on b, the kernel, the number of restrictions, and features of the regressor design unless an appropriate transformation is used. Pivotal means free of unknown nuisance parameters, not identical across all implementations. Critical values must match the exact statistic. A table for one kernel or bandwidth fraction should not be reused for another. Software output is trustworthy only when its asymptotic convention is explicit. Think of small b and fixed b as two approximations to the very same finite sample statistic. Small b gives a simpler, standard limiting law, but it leans on estimating the long-run variance consistently. Fixed b gives a more complicated law, yet it takes seriously that the bandwidth is not negligible. Neither one changes the coefficient estimate itself. They differ only in how they approximate uncertainty and where they get their critical values. When the two agree, I take that as reassurance. When they disagree, I read it as a warning that the inference is fragile. Fixed b does not solve model misspecification. If regressors are endogenous, the conditional mean is wrong, or structural breaks violate the assumed stable process. Changing asymptotics does not restore identification. The functional central limit theorem and design convergence also require substantive regularity. Very persistent or non-stationary data may need different theory. Robustness to heteroskedasticity and autocorrelation should never be confused with robustness to every failure of an econometric model. In practice, begin with a scientifically justified regression and inspect the score process rather than only residuals. Calculate standard HAC inference across reasonable lag choices, then add fixed b inference with matching kernel and critical values. Report b as a fraction of sample size and translate it into an actual lag count. If a conclusion changes, explain whether the fixed B interval widens, because it incorporates covariance estimation uncertainty. Do not present the most favorable method as uniquely authoritative. Simulation is useful for understanding the method. Generate Brownian paths on a fine grid. Construct the same kernel-based matrix functional used by the statistic, and compute many simulated test values. Their empirical quantiles approximate fixed B critical values. Numerical resolution and the number of simulations affect accuracy, so set and report a random seed and simulation size. In applied R work, a validated package is preferable, but reproducing the limiting experiment once makes the logic much clearer. A fixed B confidence interval is obtained by inverting tests that use the matching non-standard critical values. Because those critical values are usually larger than standard ones, intervals often widen. The change reflects uncertainty in long-run variance estimation, rather than a change in the coefficient estimate. Comparing interval endpoints is more informative than comparing only whether two p-values cross a threshold. A common mistake is to say that an inconsistent variance estimator must be bad. Consistency is valuable when the estimator itself is the final object. Here, the final object is a studentized statistic, and proportional random limits can cancel nuisance scale. Another mistake is to mix a fixed B variance estimate with standard normal critical values. That hybrid keeps the noise but omits its distributional correction, often producing inference with no coherent justification. The finite sample bandwidth must match the asymptotic fraction precisely. If the chosen lag count is m and the sample size is capital T, B is their ratio under the stated convention. Rounding, demeaning, and losing observations to lags can change the effective fraction. Critical values should use the effective estimation sample, not an unrelated raw row count. Fixed B makes a broader point worth remembering. Good inference does not always require estimating every nuisance quantity consistently. Sometimes we can build a statistic so that the nuisance scale simply drops out of its limit. Self-normalisation pushes that idea further, building the denominator straight from recursive estimates or partial sum paths. Adjusted range methods give yet another normalizer, one that stays steadier when variance-based constructions react too strongly to unusual observations or persistent volatility. Those approaches are what the next lesson is about. Let me start with the idea behind self-normalisation, because it is simpler than it first sounds. We build a test statistic whose denominator comes from the same growing sample as its numerator. So the unknown long-run scale cancels from the limiting distribution. The classic student t-statistic is our guide. In an independent Gaussian sample, we divide a centered sample, mean, by an estimated standard error built from the random sample variance and obtain an exact pivotal distribution. Time series self-normalisation extends that logic to heteroskedastic and dependent observations using entire partial sum paths. For regression, begin with recursive residual score sums. At each sample fraction, accumulate regressors multiplied by full sample OLS residuals. Because those residuals are constrained by the final estimate, the rescaled path converges to a Brownian bridge rather than unrestricted Brownian motion. A Brownian bridge begins and ends at zero. Its fluctuations through the interior record how recursive estimates differ from the full sample estimate, and those fluctuations contain the long-run scale needed for normalization. Kiefer's construction forms a matrix by averaging outer products of the residual partial sum path. This matrix does not consistently estimate the long-run covariance. Its limit equals the unknown scale surrounding an integral of Brownian bridge outer products. Combining it with the coefficient deviation removes both the regressor design and long-run covariance nuisance factors. The resulting limit is a mixture rather than a standard normal distribution, with heavier tails because the random denominator adds uncertainty. For an individual coefficient, the resulting t-star statistic resembles an ordinary t-statistic, but uses the recursive path-based normalizer. Its limit is Brownian motion at the endpoint, divided by the square root of integrated squared Brownian bridge variation. Critical values are therefore much larger than standard normal values. They can be simulated from Brownian paths. Using standard t critical values would over-reject because it ignores the substantial randomness in this non-consistent denominator. The connection with a conventional t-statistic is conceptual, not an assertion that their distributions are identical. Both use a random internal estimate of scale. In independent Gaussian data, classical studentization produces a student t-law with degrees of freedom tied to sample size. Under weakly dependent time series, recursive self-normalisation produces a Brownian functional. The appropriate critical values come from the latter limiting experiment. The data structure determines which studentization argument is valid. Xiao's construction makes the idea especially transparent. For a sample mean, compute the mean recursively through each date and compare every recursive mean with the full sample mean. Weight those deviations by the amount of data available, square them, and average with the proper sample scaling. The result measures the cumulative fluctuation of recursive estimates. It is stochastically proportional to the long-run variance, even though it does not converge to that variance as a constant. Under moment, weak dependence and functional central limit conditions, the recursive deviation path converges to a scaled Brownian bridge. The self-normalizer converges to long-run variance, multiplied by integrated squared bridge variation. The centered full sample mean converges to the same scale multiplied by Brownian motion at the endpoint. Dividing cancels the scale and gives a nuisance-free limit. Monte Carlo simulation of Brownian motion supplies, confidence interval and test critical values. Self-normalization is not limited to the sample mean. It works for a whole family of estimators we can call approximately linear. The idea is that such an estimator can be written as the quantity we want, plus an average of something called an influence function, plus a remainder that is small enough to ignore in large samples, means variances, autocorrelations, and quantiles all fit this pattern under the right conditions. So one normalizing principle covers many targets, and we never have to derive a separate long-run variance formula for each one. The influence function describes the first-order response of a statistic to a small change in the underlying distribution. It is not necessarily observed, yet recursive estimates can often generate the required path without estimating the function directly. Validity needs a functional central limit theorem for the influence sequence and uniform control of expansion remainders across subsamples. A pointwise approximation at the full sample is insufficient because the normalizer uses the entire sequence of recursive estimates. For a vector parameter, the normalizer becomes a matrix built from outer products of vector recursive deviations. A quadratic statistic can then test joint restrictions. Its limiting distribution depends on the number of tested components, but not on the unknown long-run covariance. Critical values must match that dimension. Numerical stability matters because early recursive estimates may be poorly determined. Implementations often trim very small initial subsamples or require that each recursive design matrix have full rank. Variance-based self-normalization can deliver improved test size but reduced power. Squaring partial sum deviations gives large influence to unusual excursions, including outliers, persistent autocorrelation, heteroskedasticity, or long memory. The resulting denominator can become large, making the test conservative. This is not proof that the method is wrong. It identifies a size and power trade-off that motivates an alternative path functional with different sensitivity to extreme recursive deviations. Adjusted range self-normalisation uses the range of a centered partial sum path. For the sample mean, subtract the full sample mean from each observation. Accumulate those centered values and take the difference between the path's maximum and minimum after scaling. The range converges to long-run standard deviation multiplied by the range of a Brownian bridge. Dividing the centered mean by this range again removes the unknown scale and yields a nuisance-free non-standard limit. The adjusted range statistic and the variance-based statistic have different limiting shapes and therefore different critical values. Simulations in the chapter illustrate that the range-based version can offer a more balanced size and power trade-off in settings where squared path variation is overly sensitive. This is a potential advantage, not a universal dominance claim. The data process, parameter, and alternative determine performance. Critical values must come from the exact range-based Brownian functional. For multivariate parameters, cross-dependence among components complicates separate ranges because each range is non-negative and coordinate dependent. Partial pre-whitening first transforms the recursive parameter vector to reduce contemporaneous cross-dependence while preserving temporal dependence. Coordinate-wise, adjusted ranges can then form a diagonal normalizer before transforming back. A joint quadratic statistic has a simulated distribution indexed by parameter dimension. The transformation must be estimated consistently, so adjusted range methods do not eliminate every covariance calculation. In R, keep the observations in order and compute each recursive estimate with exactly the same specification you used on the full sample. Check the minimum subsample size, watch for failed fits, and look at how well conditioned your matrix factorizations are. Simulate the critical values with a fixed seed, or use verified tables for the exact statistic and dimension. Then compare HAC, fixed B, variance-based self-normalisation, and adjusted range side by side. Where they differ, that tells you how the treatment of uncertainty is shaping your conclusions, so explain those differences rather than hide them. Self-normalisation changes the inferential strategy from consistently estimating long-run variance to constructing a statistic with a nuisance-free proportional limit. Its validity still rests on stability, weak dependence conditions, recursive approximation, and correctly matched critical values. Range-based normalization changes the path functional to improve robustness and power in some environments. These methods are powerful complements to HAC inference. The next lesson turns to resampling, where sampling distributions are approximated by creating many structured pseudo-samples. The bootstrap approximates a sampling distribution by repeatedly constructing pseudo-samples, re-estimating the statistic, and examining the resulting empirical distribution. For independent data, sampling observations with replacement from the empirical distribution can reproduce many features of repeated sampling. The bootstrap is not automatically assumption-free. Its validity depends on whether the resampling scheme imitates the important structure of the data and whether the statistic behaves regularly. Time series require special care because independent resampling destroys serial dependence. Begin with the root, the centered and scaled statistic, whose distribution is needed for inference. Estimate the parameter from the original sample. For each bootstrap replication, generate a pseudo-sample under an estimated data-generating mechanism. Re-estimate the parameter and calculate the bootstrap root centered at the original estimate. Repeating this procedure gives an empirical distribution for critical values, p-values, or confidence intervals. Centering and studentization should mirror the theoretical statistic, not be improvised after the simulation. Bootstrap consistency means that, conditional on the observed data, the bootstrap distribution approaches the true sampling distribution under suitable conditions. It does not mean that a finite set of replications reproduces the exact finite sample law. Monte Carlo error remains, and model or resampling error can be more important. Increasing replications reduces simulation noise, but cannot repair an invalid bootstrap design. We should separate computational precision from statistical validity when diagnosing unstable results. For a time, series represented by a well-specified ARMA model, a parametric bootstrap can preserve dependence through the fitted dynamics. Estimate the autoregressive and moving average parameters, obtain and recenter residuals, draw pseudo-innovations, and generate each pseudo-series recursively from the fitted model. Re-estimate the model for every series and form the root. This scheme is efficient when the dynamic specification is credible, but misspecified dynamics are reproduced in every bootstrap sample. An AR1 example makes the steps concrete. Regress the current observation on its first lag, calculate residuals, and subtract their sample mean. Draw residuals with replacement, generate a pseudo-series using the estimated autoregressive coefficient, and estimate that coefficient again. The bootstrap root is the square root of sample size times the pseudo-estimate minus the original estimate. Initial conditions and burn-in can matter when persistence is high, so the generation rule must be documented. Residual resampling assumes that fitted innovations are exchangeable after the dynamic model is removed. Conditional heteroskedasticity violates that idea because innovation scale varies over time. The wild bootstrap retains each residual's magnitude and multiplies it by an independent random weight with mean 0 and variance 1. Common weights include equal probability, positive and negative signs, or a two-point distribution designed to match an additional moment. This preserves a pattern of heterogeneous conditional scales while randomizing signs. The wild bootstrap addresses heteroskedasticity, but it does not independently reconstruct arbitrary serial correlation. Dependence must be handled by the fitted dynamic structure or by a dependent multiplier design. Applying independent wild weights directly to serially correlated residuals can erase the very dependence that robust inference must preserve. Always identify which part of the procedure represents conditional mean dynamics, which part represents serial dependence, and which part represents changing variance. Block bootstrap methods preserve local dependence by resampling consecutive stretches of observations. Divide or enumerate the series into blocks, sample blocks with replacement, and join them to create a pseudo-series. Moving block, circular and stationary variants differ in how blocks begin and how lengths are treated. A longer block retains more dependence but yields fewer effectively independent pieces. A shorter block provides more recombination but breaks longer range relationships. Block length is therefore another bandwidth problem. Under suitable stationarity and weak dependence, block length should grow with sample size while remaining a vanishing fraction of the sample. Finite sample selection can use plug-in rules or sensitivity analysis. Joining blocks creates artificial boundaries, which some variants soften but cannot eliminate completely. Seasonal structure and structural breaks require particular caution. Resampling blocks across distinct regimes may create pseudo-histories that are statistically possible under the algorithm but economically implausible. Subsampling uses overlapping windows without resampling observations with replacement. Compute the statistic on every or many consecutive subsamples, center it relative to the full sample estimate, and scale it by subsample length. The empirical distribution of these window-based routes approximates the full sample route distribution under broad conditions. Subsample length must grow while remaining small relative to the full sample. Subsampling is simple and often robust, though it may be conservative and sensitive to the chosen window length. A return series, such as the S&P 500, provides a useful comparison. The mean return can be examined with block or subsampling distributions that preserve local dependence. A volatility statistic may require even greater attention to dependence in squared returns. The purpose of the case study is not to crown one universal method. It is to compare how parametric dynamics, blocks, wild perturbations and windows represent the observed persistence and heteroskedasticity. Regression bootstrap design depends on the regressors. With strongly exogenous regressors, one may condition on the observed regressor sequence and resample appropriately constructed residuals, then generate pseudo-outcomes from the fitted equation. If regressors are stochastic and dependent, resampling residuals alone may break their joint relationship with the equation error. Paired block methods or a model for the joint process may be needed. Endogeneity cannot be cured by ordinary residual bootstrapping because the identifying condition itself fails. For stationary and mixing regressors, blocks can preserve joint temporal dependence among outcomes, regressors, and residual components when the full observation vector is resampled together. This broadens validity but relies on stability across the sample. If a policy change alters coefficients, a stationary block bootstrap blends incompatible regimes. Before resampling, test design and economic timing matter more than computational sophistication. A bootstrap faithfully reproduces the structure it is given, including unrecognized misspecification. In R, set a seed, store both parameter estimates and roots, and monitor failed replications. Use enough replications that simulation error is small relative to the inferential distinctions being reported. Re-estimate every tuning step that would be repeated under genuine sampling unless the theoretical bootstrap conditions on that step. Inspect the bootstrap distribution for skewness, outliers, and discreteness. Report the resampling scheme, block or subsample length, initialization, replication count, and interval construction. Percentile, basic, and studentized intervals each use the simulated distribution in a different way. Studentizing can improve accuracy when you recompute a reliable standard error inside every replication, but it costs a lot of computation and adds another tuning problem for dependent data. Choose the interval method before you look at which one happens to exclude the null, and make sure its centering and scaling line up exactly with the particular bootstrap result you are relying on. The bootstrap is powerful because it can approximate complicated sampling laws without deriving every finite sample formula. Its success depends on structural imitation. Independent resampling suits, independent observations, parametric recursion suits, credible dynamic models, wild weights address heterogeneous scales, and blocks or subsamples preserve local dependence more flexibly. No scheme handles every complication at once. The next lesson returns to economic restrictions through GMM, where long-run covariance estimation and robust testing enter through sample moments. The generalized method of moments, or GMM, estimates parameters by making sample moment conditions as close to zero as possible. Economic theory often implies that certain forecast errors are orthogonal to information available when decisions are made. These restrictions may outnumber the parameters and may involve nonlinear models. GMM provides a unified framework for estimation, robust uncertainty measurement, and specification testing when the moment sequence is heteroskedastic or serially correlated. Let the model generate a vector of moments for each observation and parameter value. At the true parameter, the population expectation of that vector is 0. The sample average will not be exactly 0, so GMM chooses the parameter that minimizes a weighted quadratic distance from 0. The weighting matrix determines which combinations of moments receive emphasis. Identification requires that the population moments change sufficiently with the parameters. Many moments do not help if they contain little identifying information. Ordinary least squares is a special moment estimator. Its normal equations set sample averages of regressors times residuals to 0. GMM generalizes this logic to nonlinear residuals, instruments, and more moments than parameters. When moments exactly equal parameters in number, weighting does not change the solution if the equations can be solved exactly. With over-identification, different weights generally produce different estimates because no parameter sets every noisy sample moment to 0 simultaneously. Under regularity and identification conditions, the GMM estimator is asymptotically normal. Its covariance combines the derivative of population moments with the long-run covariance of the moment process and the weighting matrix. Heteroskedasticity and serial dependence therefore enter through the same long-run variance problem studied earlier. A robust implementation estimates that covariance with an appropriate HAR method. Calling an estimator GMM does not itself make its standard errors robust. The asymptotically efficient weighting matrix is the inverse of the long-run covariance of moments evaluated at the true parameter. Because that covariance is unknown, two-step GMM first uses a simple positive definite weight, obtains a preliminary estimate, estimates the moment covariance there, and re-estimates with its inverse. Iterated GMM repeats these updates. Iteration can improve numerical convergence in some problems, but it does not repair weak instruments, invalid moments, or a poorly scaled objective. Instrument quality matters in two ways. Relevance means that the moments respond to the parameters strongly enough for identification. Validity means that instruments are orthogonal to the structural error at the correct timing. Adding weak or invalid instruments can worsen finite sample bias and make covariance matrices unstable. The instrument set should come from economic information and timing, not an indiscriminate list of available variables. Centering, scaling, and checking rank can materially improve numerical behavior without changing the economic restrictions. The consumption-based capital asset pricing model, or consumption CAPM, provides a central application. An investor's intertemporal marginal rate of a substitution acts as a stochastic discount factor. For each asset, the expected product of this discount factor and the asset's gross return should equal 1. With power utility, the discount factor depends on a subjective discount parameter, consumption growth and relative risk aversion. These pricing equations become population moment restrictions for GMM. To create unconditional moments, multiply each pricing error by instruments known at the relevant decision date. A constant instrument asks the model to price assets on average. Lagged state variables ask whether pricing errors remain predictable from available information. Timing is crucial. A variable observed only after the return cannot be a valid predetermined instrument. Moment validity is an economic and informational claim, not merely a condition that sample correlations happen to be small. The first stage can use an identity weighting matrix to obtain preliminary discount and risk aversion estimates. The second stage estimates the long-run covariance of pricing moments and uses its inverse. Because consumption growth and returns are persistent or heteroskedastic, HAR weighting may be required. The result should be checked for parameter bounds, sensitivity to starting values, optimizer convergence, instrument scaling, and covariance conditioning. A printed estimate from a non-linear optimizer is not sufficient evidence of identification. When there are more moments than parameters, the J-test evaluates over-identifying restrictions. At the efficient estimate, multiply the minimized weighted criterion by sample size. Under the null that all moments are valid and the model is correctly specified, the statistic has an asymptotic chi-squared distribution with degrees of freedom equal to the number of moments minus the number of estimated parameters. Rejection says that the collection of restrictions is inconsistent with the data, but does not identify which restriction failed. Euler equation errors provide an economically interpretable diagnostic. For each asset and date, they measure the gap between the model-implied discounted payoff and the value required for exact pricing. Persistent or predictable errors reveal where the stochastic discount factor fails. Aggregate moment conditions can conceal offsetting mistakes, so inspect errors across assets, states, and time. A model that prices average returns while failing badly during downturns may be statistically convenient, but economically inadequate. The Hansen-Jugu-Na-Thun distance measures how far a model-implied stochastic discount factor lies from the set of discount factors that price the test assets exactly, using a return-based norm. It summarizes pricing failure in economically meaningful units and supports comparison across models. Like any diagnostic, it depends on the chosen test assets and sample. A small distance for a narrow asset set does not prove universal validity, while a large distance directs attention to substantial pricing errors. The equity premium puzzle illustrates the substantive stakes. A standard consumption-based model with constant relative risk aversion struggles to explain the historically large difference between equity and safe returns using the smooth consumption growth observed in the data, unless risk aversion becomes implausibly high. GMM estimation and over-identification tests turn that tension into measurable moment failures. Extensions with habits, rare disasters, recursive preferences, or heterogeneous investors change the economic discount factor rather than merely changing standard errors. One extension allows discounting and risk aversion to vary with observed state variables. The pricing equation then contains unknown functions rather than fixed coefficients, and local polynomial or local GMM methods can estimate them. This flexibility may capture changes across expansions and downturns, but it reintroduces bandwidth choice and the curse of dimensionality. State variables must still be available at the correct date. Flexible preferences should be evaluated out of sample and against simpler, economically interpretable alternatives. The R case study aligns consumption, short-term interest rates, and market returns, constructs consumption growth and excess returns with careful timing, defines moment functions, and estimates the model with a GMM package. The reported example produces a strong rejection by the J-test, indicating that its selected moments do not jointly fit the standard model. The correct response is not to search mechanically for instruments that avoid rejection. It is to diagnose timing, data construction, identification, and economic misspecification. Across this chapter, robust inference has taken several forms. Spectral analysis connects long-run variance to low-frequency behavior. HAR methods estimate that variance consistently. Fixed B and self-normalisation retain random normalisation and change critical values. Bootstrap methods reproduce dependence through structured pseudo-samples. GMM combines economic moments with long-run covariance estimation. These tools are alternatives and complements, not interchangeable labels. Credible empirical work states which dependence is allowed, how tuning is chosen, and which assumptions support the reported uncertainty.